let's look at how to complete a non-standard linear programming problem using the Simplex method. So this is a non-standard problem because, as you may notice, we have two different types of inequalities. And for a standard maximization problem, we're only allowed to have less than or equal to. So we have to introduce something called a surplus variable. So anytime we have greater than or equal to, we're going to have a place where we subtract of surplus variable, and anytime we have a greater than or equal to, we'll be adding a slack variable. So first step in the Simplex method is to rewrite your inequalities into equations using slack and or surplus variables. So we have x1 plus 4x2 minus s1, because of that greater than or equal to sign, is equal to 22, and x1 plus x2 plus s2 is equal to 41. And again, adding a slack variable because of the less than or equal to sign. And then rewrite your objective function. So putting all of our variables over on the left side and all of our constants on the right. This looks like negative 12x1 minus 10x2 plus c is equal to 0. So there's our first step in our linear programming problem with the Simplex method. Step number 2, rewrite the objective function. And step number 3, turn this all into a matrix. We have 3 equations, so it'll be a 3 by and 1, 2, 3, 4, 5, 6 different types of variables, so a 3 by 6 matrix. Call this x1, x2, s1, s2, z, and a constant. So fill in all of your coefficients from your matrix. Okay, so we've got all of those in our matrix. And if we read our matrix right now, x1 is equal to 0, x2 is equal to 0, and s1 is equal to negative 1. And this is a problem. We have s1 equal to negative 22, which means one of our basic variables is negative and yields a negative solution. This cannot happen. So to fix this problem, what we'll do is take this basic variable and turn it into a non-basic variable. Start by identifying the row where your negative basic variable is located. So ours is located in the first row. Go as far left as you can in this row and look for a positive number. So if we go all the way to the left, we'll notice that we have a positive 1 as far as we can get to the left. This is our pivot column. So start by identifying which row has your negative basic variable in it or basic solution. Go all the way to the left, looking for a positive coefficient. This is your pivot column. So to find your pivot position, similar to what you've done in the past, you'll create quotients. We have 22 over 1 and 41 over 1. So we have 22 and 41. So that means we are pivoting around this top 1. We're still looking for the lowest quotient. Once we find our pivot position, the next thing we'll do is turn our pivot position into a 1. Ours is already a 1, so no need to do that. Next, we're going to have to turn these two numbers into zeros. So to turn a number into a 0, we just do opposite sign. So 1 will be a negative 1, and negative 12 will be a positive 12. Multiplied by our pivot row. So our pivot is in row 1, so these are both row 1s. And added to the rows we're changing. This is in row 2, and this is in row 3, and it yields a new row 3 and a new row 2. Okay, now we're ready to use our calculator. So the first thing we're going to do is put this matrix into our calculator. So do second matrix, or you may have a matrix button. Go over to edit. And the first thing it'll ask you for is the size of your matrix. Ours is a 3 by 6, so type that in. And then type in the coefficients from your matrix. Okay, once you're done doing that, hit second mode. It'll take you out of the program. and then hit the program button and find the one that says row ops. Choose row ops, hit enter, make sure you check your matrix to see if it has all of the right numbers. I feel good about mine, so I'm going to leave it. Normally, we would hit enter, we would choose to multiply to turn our pivot position into a 1. Since our pivot position is already 1, we are now in the point where we need to turn our other numbers into zeros. Both of these steps are taken care of in your calculator under to pivot, and we'll be pivoting around row 1, column 1. That is the location of our pivot position in the first row and the first column. So we're going to choose option number 3 to pivot around row 1, column 1. And then write down the matrix that you have now yielded. Should look like this. So once you've done this, go back and look and say, do you have any more negative basic variables? And we don't. Right now, x1 is equal to 22, x2 is equal to 0, s1 is non-basic, so it's a 0, s2 is equal to a positive 19, and z is equal to 264. So we have no more negative basic variables, so we don't have to worry about that anymore. Now we just have to worry about maximizing. And have we found a maximum solution? We have not found a maximum solution because there is still a negative indicator. So now that we're done with the negative basic variables, now we're back into the regular simplex method mode. Here's a negative indicator, the most negative indicator. So there's our pivot column. Our pivot numbers can never be negative and they can't be 0. So our only option for a pivot is right here around the 1. Normally, when we pick our pivot position, we would start by turning our pivot position into a 1. Ours is already a 1, so we don't have to do that. Now we need to turn these two numbers into zeros. To get a 0, we multiply by the opposite sign. So -1, I'm going to be multiplying with +1, and -12, I'll multiply with +12. Both of these I'll multiply with row 2. That's my pivot row. Add it to the rows I wanted to change. This -1 was in row 1. This 12 was in row 3, yielding a new row 1 and a new row 3. In your calculator, this is both under to pivot. Tell it where your pivot position is. Our pivot is in row 2 and column 3. So bring them back over my calculator. Hit enter to bring back up those commands. 3 to pivot around row 2, column 3. So our new matrix looks like 1, 0, 0, 1, -3, 2, 0, 1, 0, 1, 1, 12, 0, 0, 1, and 41, 19, and 4, 92. So now we don't have any negative basic variables anymore. We also don't have any more negative indicators. We have completed finding the optimal solution for this linear programming problem. Our solution is when x1 is equal to 41, x2 equals 0, s1 equals 19, s2 equals 0, and z is equal to 492.